So here's a question on Bayesian inference. Let's say you're interested in the first year GPA of a set of students at the University of Manchester, and you and your three friends are sort of thinking about it. You think the average is 47, and your three friends have different opinions. So let's call that average mu. First question is, what is the parameter of interest? That is mu. Okay, we are after that mu, and what we assume is that this parameter isn't really fixed, it has a distribution. And that's the difference when we're doing Bayesian inference to frequentist approaches. So mu has an unknown distribution. And what we are really after when we're doing Bayesian inference is that distribution, a distribution of mu given a set of observations of data. So this is our final aim. This is what we are shooting for. So now if we have that information, what is the prior distribution? We'll see later. We need the prior distribution notationally. That's the distribution of mu without information of any data. Now in our case, it's perhaps easiest to think of a little sort of number line here. Your guess is 47 and your friends guess 52, 57 and 67. Now in reality, of course, this parameter mu could take any sort of values and not only these four different values. So really that distribution should be a continuous distribution. Okay, and both the prior and what we will later call the posterior distribution should be continuous distribution. But for simplicity in this example, we shall restrict it to be a discrete distribution so we will only consider these four possible values. We will not entertain that mu could take any other values. That's of course unrealistic, but the idea of Bayesian inference can nevertheless be illustrated using this. So what's the prior distribution? Without any other information, we'll have to say each of these four values are possibly equally likely. That would be a sensible prior distribution here, and that would be 0.25. Right? Four possible outcomes, each equally likely. So the distribution for these is 0.25. We can write it down formally. The probability that mu is equal to 47 is 0.25, and that is the same as the probability that mu is 52 or 57 or indeed 67. That's how we're gonna start. So let's expose this setup to some data. This is now the next step, and then we'll see what happens in Bayesian inference. So here's the data. We have a sample of 21 students. Here's a histogram of their first year GPAs. And what does that mean? If we look at this histogram, possibly see that the sample average X bar is going to be somewhere between 60 and 65. So let's say approximately 62. That's as much as you can say from this histogram of data. Now we're being asked to describe how Bayesian inference uses this information to change the prior distribution of mu. At the core of Bayesian inference is this relation. The posterior distribution, the distribution of mu given data, is proportional to the probability of seeing the data given a value of mu times the prior distribution. So just to make that clear, what we have back here, that is the prior distribution. This is what we call the likelihood of the data, and this is what we will call the posterior, and that's what we are essentially after. Now, given we have a discrete distribution with four possible values for mu only, we'll have to evaluate this at four possible values only. Now that's convenient. Really, you should evaluate it at an infinite number of possible values. So we said previously the prior for each of them is 0.25. So let's look at the likelihood here. And let's start with 47, values of 47, which is about here. And let's actually show where all the 4 possible values are. Now these 2 values, 47, 52, they're really, it seems to be quite unlikely that if the real mean was any of these, that we would see the data which we see. So they're not so likely, which means that the posterior distribution will go down relative to the prior. The other 2 values, 57 and 67, seem to be sort of equally plausible, and therefore we will see that relative to the prior, the posterior distribution will go up for these 2 values. How do we say that in words? What we do? Well, we use the observed data to evaluate the credibility of the proposed values for mu, the 4 possible values, and then we will adjust the prior probabilities accordingly, meaning that we will increase it, or we will get an increased posterior for the values of mu for which the data were more likely. So that's the basic idea. So let's put that into practice. We have our 4 values and the prior probability of 0.25 for each of them. So how credible was 47? So we already discussed that. That was extremely uncredible. Okay, so this is, the data do not support the idea that mu could be 47. Okay, it's very unlikely that the data were generated by this. Now 52, it's also not really supported, not as extreme as 47, but it's really not supported. If you look at the data, we'll go back to the data in a moment, you will see that at least 75% of the data are actually larger than that mean. And from a sample of 21, that would be quite unlikely. So let's look at the data. So if we look at the mean of 57 about here, the data to the right, the data which are larger, is about 75%. Now the other 2 values, 57 and 67, so here and here, now both of them sort of look equally credible. So 57 and 67, they're really quite credible alternatives, certainly the most credible alternatives of our 4 values. So what does that mean for the posterior? The most we can ask for with the information given is educated guesses here. And that's what we'll do. So that first value, 47, that was really not supported. So let's give it a very small posterior probability, 1%. 52 was a little more likely than 47, but still very small. That leaves us 94%, and let's split them equally between 57 and 67. So that would be a guess at the posterior. Now actually, if you have the data, which I have, and do all the calculations, what you get as posterior probabilities, and you couldn't get that with the information given, was actually 0 for the first 2, and 61% for 57 and 39% for 67. So it turns out the average, the sample average, is actually a little closer to 57 than 67, which is why it assigns a large probability to 57. But you couldn't see that from just looking at the data.